Our next speaker is a colleague from ETH Zurich, Professor Domenico Giardini, a seismologist and also one of the co-PIs on one of the 12 projects that we are leading under the HP2C platform that you have just heard of. So imagine this is one of 12 projects that, with the help of Uzi, were created here. Please.
Signore e signori, buongiorno a tutti. I am not a computer scientist. I'm just a scientist. But like many scientists today, I desperately need computers. We need data, we need laboratories, and we need computers. And today, I will show you examples on how our science is progressing. Can we get the slides? I will talk about high performance computing in solid earth geophysics, that is in what we do inside the earth, and in seismology. Not everything I will show there comes from me. It comes from a range of colleagues, some of them in my group, some of them in general fields of geophysics. And they come also from the Swiss Seismological Service, which is located in Zurich. First of all, let me start with thanks. I'd like to thank. I'm honored to have been chosen as one of the many professors from Zurich that can show you his science, and it's for me a real pleasure and an honor to show you our science. And then I'd like to thank all the colleagues that also contributed, and mostly I'd like to thank all the colleagues here, formerly Manno, now in Lugano, or the colleagues at the High Performance Computing Park and the Informatics Dienst in Zurich. Without them, for a poor scientist like me, it would really be impossible to develop all of this. And this is an extremely important cooperation. Professor Eichler before was talking about brains, not my brain, it's their brain that helped us to develop our ideas. This is extremely important. Without that, it wouldn't go. I'm a very lucky scientist. This is the object of my research, what everybody would want to have. The only thing, I don't look at the surface, I look below, and life gets immediately difficult. I will show you how modeling, and in particular high-performance modeling, has become a key ingredient in today's scientific progress, sometimes as important or superior important than data. Reason being that it's extremely difficult to get data out of this body from inside the body. What we would like to do is to open it up, but that's still beyond the ETH possibilities, so we really need to find other ways to actually work on this. So we have the challenges, no direct access to the interior other than a couple of tunnels or boreholes. 70% is covered by oceans, uneven data coverage, uneven data availability. A very heterogeneous structure inside the Earth, very large scale range of properties. You have to think what I'll be showing you today are processes that range between a duration of 1 second and 100 million years. Length scales that go from 100 meters to 10,000 kilometers. And horrendous range of temperature, viscosity, pressure, and all other physical characteristics of what we have under our feet. So to put all of that and try to image it and put it into a modeling framework, it's really at the top end of computing science today. One way we have to look inside is seismology. Classical domains or new domains of computational seismology are the numerical simulation of seismic waves, global seismology, the structure, earthquake source dynamics, earthquake hazard and scenarios, which is what we need for protection of our society, exploration for oil, gas, energy reserves, and verification of nuclear explosions. I will take you through a tour of all of this. I will not treat nuclear explosions, but the rest I will try to give you a general panorama where we stand. We will start from data, meshing, on how do we parameterize the world we live in. We will look at scenario propagation of waves in complex media. We will look at exploration techniques on global structure of the Earth and how we retrieve how the structure is built, on how an earthquake source behaves and what happens during an earthquake. I will not go all the way to protection of society, but this is a clear aim and scope of some of our researches and one of the mandates of the Swiss Seismological Service, which I had the fortune to direct for 15 years. In geophysics, as in imaging technology, when you go to your doctor and do a TAC investigation, we deal with both forward modeling and inverse modeling. Forward means you start from an existing Earth model. The starting model that you have could be extremely wrong. and then you generate synthetic data out of it. If that model were correct, how data would look like. You produce synthetic data. That's the modeling part. And then you compare and you minimize the distance to real data that you observe in the field. Doing this is so-called inverse problem. From this, you derive a refined Earth model, and you start again. So what we do is we continuously improve the data that we have here by collecting new data, and we continually improve our way to modeling forward in order to generate more advanced synthetic in a very complicated Earth model. And all of this is a big engine, and it runs here, because the more we have data, the more we advance our Earth knowledge, the more we need better computing tools to simulate. First, start meshing. I mentioned it before. We need a mesh. We need some formulation. I will not go into any computing, but just to show you how difficult it is and how complicated it can be. This is Grenoble, the sedimentary basin in Grenoble. This is how most of you and I would see it, but there are some computer scientists here. They see it in a different way. They see it as a very complicated mesh. And here we are interested in simulating what an earthquake would do on the sedimentary part of it. The city of Grenoble is here. So you have a general mesh through which you propagate your seismic wave. You have a much better resolution mesh just for the part below where you're interested in. And on top of that, you add the actual sediment part. Even more detailed than this, more detailed than this. Once you have the whole thing, you bring it together, and you divide it in a number of domains in order to feed it through parallel computers. To do this takes 2 years. These are not just points. For each of these points, you have to specify the physical property, the density, the attenuation, the velocity. Otherwise, you can't propagate seismic wave to it. So generating today advanced models, it's really very complicated. The challenge is really also generating a realistic mesh. That depends on how many data you have, what's your knowledge of the underground, what is the frequency of the waves you want to propagate through it. Very complex is also the seismic source. This is, in yellow here, it's a fault that broke the western part of the Northern Anatolian Fault in '99, the so-called Izmit earthquake, the last large earthquake we had in Europe, a magnitude 7.6. This is the Marmara Sea. If you look at the 100-kilometer scale, it's complex. It has bends, it has interruptions. When you go and you look at an individual part at 10-kilometer scale, it's also complex, bends, interruptions. When you go at the 1-kilometer scale, it remains complex. So we have such a fractal complexity in nature which we cannot escape. I could drive you down to the 1-meter scale or the laboratory scale. It would remain equally complex. And normally we make approximations, but when we make approximations, we pay a price. We make approximations because we don't have enough data, or we are unable to model. And so we collect more data and we improve our modeling techniques in order to come down to the scale that is really relevant. Because your single building scale, of course, it's just a little piece of this 1-kilometer scale. The challenge then for us is to understand the behavior of faults and the controlling mechanism of earthquakes. Frictional properties, strength, heterogeneity, material interfaces, and so on, to generate a realistic earthquake. An earthquake is not a point. An earthquake breaks a fault or a fault system, and we are trying to simulate all of this. Fault is a complicated, non-planar set. This is a Landers earthquake in California, with branches of faults around. And what we are trying to understand is, given the stress conditions of the faults, we are trying to simulate. And our best physics goes into this, because fracture mechanics is a very complicated branch of physics. You have to think that this fault has been charging for 10,000 years. And then in 2 seconds, it goes. And so it's extremely difficult to model because the time scales of loading and discharging are very different. And we're trying to understand which properties are loaded from the tectonic stresses and how this will then propagate and will allow the faults to get bigger. We have made great strides in the last few years thanks to modeling. And you have to think that this is only the surface. The fault at depth we don't see. We don't have any way to see it. We can only model it by seeing what waveforms it generates at the surface. Now, this may seem like a good scientific achievement, but I can assure you that it's not purely academic. The Izmit earthquake we were looking at stopped here. This is the next fault that is going to go. It's the last segment of the North Anatolian Fault that has not gone in the last 300 years. This is the city of Istanbul, 15 million people. This is the potential for the fault that you have there. You have earthquake, large earthquake in the past, but not as big as the whole fault could give. What we are interested in is to understand which one of the scenarios which are dangerous for Istanbul, because it serves also for early warning and for activation of measure protections. And these are all simulations. We do hundreds of them, this in particular in my group, to try to understand, given the conditions of the faults, the bands in the fault, what happens if the fault starts here, or here, or here, or here. And you see that in some cases, for example, an earthquake starting on this part of the fault would die immediately. The conditions are such that it would not be able to propagate. But an earthquake starting here would propagate and eat up the entire fault, generating tsunami and so on. So a detailed knowledge of the fault allows us, with the immediate knowledge of where the hypocenter is, to activate very rapid alerts for the city. But you need a detailed modeling behind that tells you how the fault will behave. Now, let me get to earthquake scenarios. Earthquake scenario, if you want to have your shaking, you have to have your models of how the wave propagates. I showed you how we generate them before, and realistic model of the seismic source. You embed your source inside the mesh where you propagate the waves, and you let it go. Now, that seems simple. We need to couple realistic earthquake source and wave propagation. We want to predict shaking near faults. I will show you the results of the Terra shaking. This is a repetition of the 1757 earthquake that hit Southern California. There were about 3 people living then at that time. Today, it's a different story. You have Los Angeles, San Diego, and so on. We want to know exactly near the fault what happens, because this is the big surprise that we had in the last few earthquakes. We saw that near the faults, accelerations are much higher, the ground motion, than what we expected before. We need to understand why, and I will show you some reasons. We want to do accurate forecasting of hazard and risk scenarios for specific regions, rapid modeling of earthquake shaking. What we cannot do yet is to interface something like Lugano, the CSCS, with the real-time acquisition of data so that we can calibrate the scenarios that we run together with the real time. That's a challenge for the next 10 years. And then, of course, provide input for application of social relevance, building code, loss estimate, and so on. Now, how big is a simulation like this? It's horrendously big. That's an M8 earthquake on Southern California. The mesh size is 500 billion points, so around 500 billion points. For each one of them, you have to specify physical properties. Why do you want so many? Because you want to predict waves up to frequencies of engineering interest, the one that will be an interest to your house, so up to 2 Hz. This took the Jaguar computer, which is the largest available today, 24 hours, running on 220,000 processors. Of the team of 20 people that work on it, 1 is in our group. What is the challenge? Simulation size and complexity. This is today's limit. The size of the input per se, the source plus the mesh, is 7 terabytes, and the output is 4.5 terabytes. So those of you that use computers will understand that these are sizes that you cannot port. You cannot load them. You cannot email them. You really have to be there. And if you want to increase, if any factor of 2 increase in resolution, in frequency, or whatever requires a 16 times increase in computation capacity. That's how such a scenario would look like. This is a scenario where the rupture starts from the north. It goes all the way to the south. Professor Eichler was right in saying that we got used to animations these days. You see them all over the animations. Any movies that you see is not real anymore as animation. This is not an animation. This is just plotting the parameters that your house will be subjected to after the Jaguar has run it for 24 hours. Let me run it back, because there are a lot of interesting things here. And I'll try to demonstrate to you why we want to do this. The earthquake starts, and it starts with a big bang when it comes to the surface. Once it starts propagating, we see immediately an effect that we have for long expected, but not really seen. You see it, let me, 1 second, I need to stop it. Otherwise I can turn around. Big amplitudes here are connected to this V front that you see in the back. That's the same that you see after an earthquake, after a plane goes supersonic. It means that the rupture here, because of the property below, there is a very strong crust below. It's propagating at the speed which is beyond the so-called VS wave. So it goes supersonic. And when it goes supersonic, it generates a big peak in front, exactly like the booms that you hear when a plane goes by. And the typical signature is the V in the back, exactly like a plane would do. Now, we had suspected that a lot from our theory it comes, but when you see in the modeling, so what I mean is that when you load a realistic Earth model and then you see it generators, then you understand why in a certain area you have huge damage. Something else that you notice is something that you know in physics is called the Doppler effect. We call it directivity here. If you sit in the back of the earthquake goes away from you. You don't have essentially any damage. It's like a train. When a train comes toward you, you hear a lot of noise. When it goes away, you hear less noise, because all the waves produced by the train come to you at the same time. It's extremely important for such size of earthquake. When we keep going ahead, from here, there is something else that we immediately see. After the earthquake passes Los Angeles, what we get to see is that the earthquake keeps going ahead. The big front of the fault is here, but Los Angeles keeps shaking. Why? It's a basin full of sediments. It keeps resonating. The waves get trapped there, and they have nowhere to go. They simply stay there. It's like when you generate a wave in your bathtub. Unless you really generate a big one, then the water spills out. The water will stay there, and the wave will go back and forth. This is what happens in Los Angeles. There is another such basin. You see it immediately in the simulation. Once your simulation keeps going ahead, the basin in Palm Springs will get activated. You see that the earthquake is long gone, but Los Angeles is still shaking. And Palm Springs will do the same. Of course, this is the two biggest areas there, the two biggest cities. Why? Because it's flat. It's easy to build. It's not granite. It's sediments. Anybody would build there, like anybody would build on the lake sediments. It's an obvious one, but this is what you get for earthquakes. Now, it helps a lot for us, and ultimately for you, to look at what happens inside. So this is the same simulation. Actually, this one is from the south going north. But we display both what happens at the surface and the shakings that we have inside the first 15 kilometers of crust. And here, again, we learn a lot, because we have absolutely no way to see any of this. So you see that we have the shaking in Palm Springs, which is dominated by a very shallow layer, while in Los Angeles, the basin is still deeper. So we begin to understand how the waves go in deeper layer and upper again, and we see it out of simulation. We have no way to see it otherwise. I was mentioning before, it's important, directivity. This is the same earthquake. This is Los Angeles. The same earthquake, only starting from here and going south. The same earthquake starting from south and coming here. Exactly the same property of the earthquake, only we run it in two different directions. And the shaking in the LA basin is completely different. Take Montebello. Montebello would get 8 centimeters per second here. It's very difficult to really position where the risk really is. I'll show you a simulation for Basel. Basel sits here. Here you have the Rhine. The Rhine falls into the Rhine graben here. Falls in the sense you don't see it, but enters in a different domain. Here is purely rock, the tabular Jura, and here you enter in the sediments of the deep Rhine graben. It used to be a place where Europe started to open, and then it stopped, for reasons that we don't know, but the fact that it opened, it filled up with sediment. And the fault of the earthquake that destroyed Basel in 1356, you see it, it's here. This piece here is the fault of Rainer. Now, if you generate a synthetic scenario, we generate actually hundreds of them from various directions, with various properties of the fault, various directivities. This is what you get. This is coming from the east, just east of the city. And what you can see is on rock, the earthquake is long finished, but here it will keep shaking. The waves are trapped inside the basin, and it keeps shaking. It's a question of topography, thickness of the sediments, and trapping of the waves. How do we use that? We generate many scenarios with earthquake, south, east, west, various depths, and so on and so on. We are trying to identify, and here I show you some examples, those earthquakes that have the right combinations to trap waves. So the majority of them will not do much. They will shake, as I showed you before. But you have those unlucky earthquakes. And in this particular case for Basel, there's an earthquake located southwest of the city, propagating into the city, which trap wave near with very high amplitude near the end of the graben. These are the worst possible scenarios that we could have, and we are trying to understand what probability is there that the city gets hit by this earthquake rather than by this earthquake. In Kobe, we have seen that in 95, 260 billions of damage in Japan, and the damage was a strip 500 meter wide and 6 kilometer long, not more than that. The big damage was that. And we try to understand where in Europe, not only Switzerland, we have such conditions. Let's go to another dimension, seismic exploration. Seismic exploration is what we use for oil, gas, resources. It does not look like much. It's a ship, 2 ships. Here you have emitters of the source. You see here what you do is that you cannot wait for earthquakes to emit waves. You emit your own waves. So these are emitting waves here. They go down, and here you have streamers. Streamers, these are 6 kilometers long, each one of them, and are towed. And they collect all the waves that have gone down, have penetrated in the sediments, and come up again. Now, this is the largest moving object we have on Earth. So man, when it looks for oil, really goes to a distance. And of course, you have another one next by and another one next by. So these are huge operations. Just to give you an example, Schlumberger, give you a number, Schlumberger is not an oil company. It's only a service company for oil companies. This has 180,000 employees all over the world. Because, of course, oil and gas search is big. Now, I'll show you only one of the challenges. Precisely map and quantify oil and gas, bear information, estimate, research, drive drilling and operations, extractions. Salt layers. Salt layers are promising traps, particularly different to image. They're awfully complicated because this is how salt accumulates inside the sediments. When the sedimentation goes, the salts will be trapped by water, and then it will mix with the sediments. And we need to map very precisely something like this because your oil engineer wants to know, should I drill here, here, or here? An oil drilled at 4 kilometer depth costs you 50 million, and you have to hit it right. Because in the end, we pay a price at the gas pump. One such modeling to show you how the seismics is done. Again, very complicated waves. Let's track it back. Let's try to track it back. Good. You see that when the first wave hits the salt body, it will immediately diffract. One goes up, one goes down. And then when it hits the oil-bearing the structure, which is here, it will emit a weak signal. And this is the signal that we're trying to identify, which comes up again, and it will come to the surface. At the surface, you have your streamers recording all the waves coming up, and you have to go back and track from where each one was coming. Another such simulations. I just want to show you the complexity. There are waves which get refracted, reflected, transmitted all over the place. After a while, you have a noise field. And you have to pick in that noise field those signals that really tell you, yes, I have a salt trap. How is my salt trap, and where should I try? Where is exploration today? You don't have to follow all of this. You just have to follow numbers. The traditional way of doing exploration was to track the arrival time, the time in which these phases arrive. And then we moved in migration. That's 100 times more time consuming the computations. If we want to go to full waveform inversion, you fit the entire waveform, so including amplitude and phase amplitude. So not only the arrival time, you need 1,000 times more complication. If you want in the acoustic wave, and in elastic, you go to 100,000 more. So it's very rapid, the escalation. Now, where are we today? We're here. The limit today, it's in between time migration and acoustic full wave inversion. We begin to do some acoustic full wave inversion, but we're still far away. As you see, there is still a factor of 1,000 to go until when we can fit the waves. Now, elastic full wave inversion, it's working in global seismology. This is one simulation from global seismology where we can track waves going around the Earth. Why we do that? We do it because we are interested in understanding what the structure of the Earth is. Waves like this, after the Tohoku earthquake, the last Japan earthquake, this is exactly the waves that get generated. They get around the world and then go around again, and then again, and again. Switzerland was going up and down 3 centimeters after the Japan earthquake. You don't feel it because it's 2 minutes up and down. So you don't feel it. But the whole Switzerland was going up and down. And these waves are, of course, a reflection of the energy released. This particular simulation starts from Crete. We block it here. Here the waves encounter Tibet. Tibet is a big, thick piece of the crust. And so it disturbs the wave. The wave, there is a secondary wave which is generated, and this wave slows down. Once you keep going, the end of Tibet, the Burma corner, generates its own waves because this is where the energy arrives at the end and it gets released again into the medium. And so on and so on. The wave go around the Earth and come back, and they carry the complexity signal. So you can see it. There is a complication of Tibet marked in the first wave and in the second wave coming from here. This we use to generate internal structure of the Earth, to map how the Earth is built inside. This is just an animation. It shows different images. So using seismicity, we map which one are the cold air inside the Earth and which one are the hot air inside the Earth. What do we need it for? We need it as a driver to understand the structure of today's Earth, and that helps us understanding how the mechanism inside the Earth is. Oops. Sorry. Can't hit it. Apologize. Okay. I'll skip the animation. It's confused. So we need to understand how the Earth works inside, and we are interested in seeing how it evolves over the last millions of years to understand, for example, the structure of the Alps. So we map, using plate tectonics and the internal structure, what happens to our plates, oceanic plates that sink below. Why does it have any relevance? Because when the plate sinks, they carry rocks which have water inside. They go down, like the Pacific plate under Japan. When rocks carrying water arrive at 150 kilometer depth, they melt. When they melt, they come back to the surface. They generate volcanoes. So we need to understand how the internal part works in order to understand the generation of volcanoes. That's Naples in 1794. That means that's a Vesuvium. Naples was here. It's far enough away. You see the plume, the ash falls, the pyroclastic flow. That means the flow that remains close to Earth. This is essentially molten rock, gas with a lot of rock content, extremely hot. Naples today, you see the wharfs of the harbor, surrounded by volcanoes. That's Vesuvium, that's Capri, not a volcano. This is Ischia, a volcano. Procida, the Campi Flegrei, that's the most dangerous of the volcanoes they have there. You would wonder why people would want to live here. That's Vesuvium, the last eruption in the Flegrei, and the last eruption in Ischia. But that's actually how Naples really looks. There are 3 million people living around here. And what we want to understand, and we need it, of course, not only for science, is how the next eruption will look like. So we study the physics, we study the geology, the sedimentation of the former eruption, we study the chemistry, the explosion part, and we model. We generate models. We want to see, this is not the Vesuvium, this is another volcano. We want to see what happens when the plume goes up, the ashes fall, and the pyroclastic flows get generated. The best tools we have is modeling. This is not done in Lugano. This is done at Cineca in Italy, the highest supercomputer center in Italy. And this is what you get. You get the plume that goes up. The ashes become unstable after a while because they cool down. They start falling down. The plume continues to emit. The pyroclastic flow go down. This area, just the area so-called red zone around the Vesuvium, the first evacuation level is 550,000 people. This entire picture took 20 minutes in real time. That means not to compute. In real time, it would take 20 minutes to hit the entire periphery of the volcano with pyroclastic flow. Those of you who have been in Ercolano have seen that Ercolano was buried by 10 meters of such molten gas and rock. And this is what simulations are all about. The evacuation plans of the Vesuvium are based on simulations. I don't have conclusions, I have recommendations. So take responsibility for them, not my collaborators. I would advise to fix midterm meaningful and sustainable targets. Fix it, 5-10% capacity of top tier praise, and stick to it. So the petaflop is good today, it won't be good 5 years from now. Stick with the rate of growth that allows Switzerland to remain at whatever target you fix, 10%, 5%, this will help drive the scientific development behind. HPC should not be reserved to a few. Implement measures to ensure a hierarchy of users and sustain progress with the whole community. There is a risk that the petaflops, you have perhaps 10 people that will be able to reach it. At hexaflop, when it comes in 8 years, 6 years, we will have 2 people reaching it. So we need to make sure that various disciplines are exposed to the power of high-performance computing. Ask the scientific domains to give you their scientific roadmaps and help them because they cannot, too many individual people alone. They cannot each one develop an edge performance computing strategy. So helps in doing it. Enable access not only to Zurich, because this you're already doing, not only to Lugano, but access to global HPC infrastructure. We are running codes in San Diego, in various parts of the globe, but of course, you need a big group behind to do that. It's not obvious that everybody can do it. So help form consortia for community software development. One of the HPC2 programs that we're running, we're doing one development. As soon as Princeton learns that we're doing it here, they stop. They don't do it anymore because we do it here. And they do developments that we will use. Some of these developments require global efforts, and only CSCS can help in doing it. If we all do it alone, it's too much. Invest in programs joining scientists, computer specialists, for example, HP2C. And help not only with the codes themselves. I showed you imaging, meshing. These are tremendously difficult enterprises. When a graduate student spends 3 years to generate the mesh, it's useful, but then he has to do the science with it. And so help with imaging, meshing, storing, handling of synthetics, real-time data simulations. I will leave you with one animation, because I'd like to take you to another planet. You have all seen that 3 weeks ago, Curiosity landed on Mars. And 10 days afterwards, NASA announced the next selection of the mission for 2016. The mission is called InSight. It will look like this. InSight doesn't have any rover, won't go around, but will deliver a package with the seismometer, heat flow measurements on the surface of Mars. That's how the landing will look like. We won't be there. This is an animation, of course. It's not a simulation. Once it goes down, it will look where to land, and it will start installing its own instruments. Now, the seismometer is developed in Europe, and the entire electronics for this mission is developed at ETH Zurich. So we will get pictures of the Swiss flags and of the ETH logo from there. And after a few days, we will also get waveforms from Marsquakes. And after a few days, we will be here for the modeling. Thank you for the attention.